Hello everyone, welcome to the video on DFT for phasor calculation in harmonic analysis. In the last video, we studied how to simulate the nonlinear system for and how to store the sampled data into the workspace. Here we have taken 128 samples per cycle. So I'm making this n is equal to 128. First, I want to convert your raw data. So if you go into the workspace, whatever the saved values of IA, that saved values of IA will appear as 1 as to 1 into 641. So it is in 3D dimensions. So I have to convert that data into the column vector. Okay, so converting this row data into column vector, let us assign x data as IA, all values of all 3D, then type x is equal to x in bracket colon and single inverted comma. So due to this, what will happen? This x is first x is the row vector, then next x is the your column vector. So it is converted into the column vector. Let us calculate the length of this x. The length of this x is equal to maximum of length of x. So if we implement this command, L will be equal to number of samples in the x. So how many samples are in the x? Let's see in the workspace. So it is a 641 sample. If we run this much code, I will get it is 1 into 641. Now we have to implement DFT for this. So let us assign one x variable, capital X variable, as zeros from 1 to n. Here I am using the capital X for DFT calculation. Next we will see how to implement the DFT. For DFT implementation, I want harmonics order from 1 to 20. So I am giving the first for loop from 1 to 20. It will calculate the harmonic order from 1, 2, 3, 4, 5, like up to 20. That is the fundamental, third harmonics, second harmonics, third harmonics, likewise. Then this is the implementation of the DFT. The equation of the DFT is, okay, so let's see what is the equation of a DFT. In a DFT, if you want to calculate, so let me take another color. Okay, so I want to calculate the x of k. So x of k is equal to summation of n varying from 0 to n minus 1 x of n into e raised to minus j 2 pi k n upon n. So I want to implement this equation where this k is also varying from 0 to n minus 1. So the length of this k is up to n, whereas the length of this x of n is also up to the n. Okay, so it is up to n. So n length, n is 128 in this case. So here I have assigned k is equal to 0 and maximum value of the k is the length of L minus n. So k can be varies from 0 to total length minus n. So it is varies from 0 to L minus n. So first I will assign the phasor x of m plus k as a 0. First I have assigned it a 0. Then n should be started from a 0. But I want a recursive DFT, so that I am starting this n is from the k. But initial value of the k is equal to 0. So it is the windowing technique. In the first window, to implement this part, the first window will start from a 0 and it will be up to n minus 1. So k is equal to 0 to n minus 1. In the next window, one sample is excluded and one sample is added. So one, it starts from when the k is equal to 1, it will start at 1 and end at n. When k is equal to 2, it starts at 2 and end up to n plus 1. So this will be implemented like this. So here I have added x of mk plus 1 with x of n plus 1 exp. Exp means e raised to minus j 2 pi n into m. So you have here we have to give the harmonic order, which harmonic order you want, and that data is in complex form. This loop will run in the complex form. From that complex number we will calculate the magnitude and angle. To get the phasor, the DFT should be multiplied with 2 by n. It is absolute value of this summation, and we'll get the angle over here by the angle command. So here the magnitude, the mod of x you will get with respect to m, okay, with respect to m, and here we will get the angle of x of m with respect to harmonic order. Now we want the average of this all magnitude and angle. So let me erase all this. Next, I want to get the harmonic order. So I will get the harmonic order. The harmonic order, I want to take the average. So k is varying from 1 to 10. Instead of k, you can take m also. So because we initially we have assigned m, so you can take m also. So x of m, m, or you can take a k or x of a. So this will give a magnitude and this will give angle. The mean will calculate the average of the harmonics. So from the first order to 20th order. So first order means your 50 hertz signal, second order means 100 hertz signal, third order means 150 hertz signal. Likewise 20th order means 20 into 50, so it will go to 1000 hertz. So that harmonics up to 1 kilohertz will be calculated in this case. So this will we have a harmonics. Now let us display the given data. How to display the given data? That is, we want to do the plot of this now. Before the plot, we'll do the THD calculation. The formula of the THD, total harmonic distortion, is given by under root second harmonic square plus third harmonic square. Likewise, we have to go up to 20th order harmonic current divided by I1 means fundamental component current. In short, the formula is summation of harmonic order, let h varying from 2 to n or 2 to 20 here in this case. Uh, this is under root I h square upon I1. Okay, if you take the total root, then here it is I1 square, but we are taking I1 in the denominator, so need not to take I1 square in the denominator. So this is the formula of THD. So let us implement this THD formula over here. So THD formula is implemented here. The THD is the square root of sum of xm varying from 2 to 20 individual component square. So magnitude square into 100 to get the in percentage. Xm of 1 means it is a fundamental. So here you will get a sum of harmonic square component, square component sum, and here it is divided by with the fundamental component. Now calculating the total harmonic distortion. Total harmonic distortion will display up to the decimal point 2. That means we want it is just like 10.10 or 10 point 2 digits up. We want to display the output up to the 2 digits, so that's why it is implemented with the 0.2f%. So and instead at the place of 0.2f we have to display the value of THD. Here we have used the sprintf command to print this value. Now after this we want to plot the data. Okay, so we want to plot the entire result. So let's see how to plot the entire results. Now we'll see the plotting area. To the plots the current waveform, we'll create a subplot. So what is this subplot? In this subplot, the first plot, I want the waveform of current. Here I want the waveform of current. Waveform is always with respect to time. I want to plot the instantaneous values of I. In a second case, I need the sampled value. So sampling of this current 128 samples per cycle. So with respect to sample number, I want to display the IA. In a third case, I want to display the harmonic order. So let's say harmonic order is H. So harmonic order 1, harmonic order 2, harmonic order 3 up to 20. What is the magnitude as a stem plot? Okay, so fundamental, second order, third order. Likewise, I want to display. Here it is a magnitude of IA, or we can say magnitude of X in our case. Here I want to display the angle of this IA with respect to the harmonic order. So I need total 4 graphs. So there are 4 rows in one column, 4 rows and in one column. This is the first graph, this is second graph, this is third graph, this is the fourth graph. Hence, let us implement the subfigure command over here. So how to implement the subfigure command? 4 comma 1, that is a 4 row, number of rows are 4, number of column is 1, this is the column, and here we want a figure number. So figure number 1 for this, here it is a figure number 2, figure number 3 and figure number 4. Likewise we are going to implement this. So if we look here, so here I have implemented subfigure 411. So timing is varies from 0 with 1 divided by 50 into n, that is 120 sample per cycle up to the 0.1 second, because my simulation is end at the 0.1 second. Here time vector is created from 0 to 0.1 second with step size of 1 divided by 50 into 128 samples. Next we'll plot time versus x axis, time versus x data with the line width 2, so its thickness of the line will be 2. X-axis label is a time in second, y-axis label is a current in ampere. Let's turn on the grid. Name the title as a current waveform. Axis we will keep a padded, so that with the padded command it will keep some space around the axis, so plot will be clearly visible in that case. If you give the tight axis, then plot may not be visible clearly. Now, second plot is the sampled waveform. To plot the sampled waveform, we have to go with the stem plot. Stem of x with line width 2, sample number, y is the current in ampere, it is a sampled current, axis is again padded. Now plotting the magnitude of harmonic order. So this is the third graph. Third graph is we are plotting the magnitude. So x of m, line width 2, with respect to harmonic order, we want to print the y of label. So it will give you the stem plot like this with respect to the harmonic order. Here in the fourth one, we have to plot the angle of the x of a in radian. So harmonic order, and here it is angle of current. So if you type like slash angle, then in the output you will look like this is angle of current. Okay, so slash angle will directly print the symbol of angle in the figure window. Now let's come to the next one. So title for this is what? Harmonic spectrum. Here magnitude, and here it is a phase. Axis is padded. Now set the GCF units in centimeter. So we want 20 centimeter by 20 centimeter figure. The font size we will adjust to the 16 points. Whatever the fonts you can adjust to 16, 20, whatever required font size, or 12 font size in the display of the figure. Now let us run this file. So I'm running this file just to check the output. Here you can see the total harmonic distortion in the current is 28.18%. This means waveform is not a pure sinusoidal. So if we see the graph of all this, so you can observe the current waveform is not a pure sinusoidal, it is a stepped waveform. It's a sample, so sample is very too near, that is 128 samples per cycle, so that it is not clearly visible. So if we zoom this window, then it will be clearly visible for you. So you can see here the harmonic order, the fundamental harmonic is equal to 0.71 0.719. So likewise different harmonics are displayed over here. Okay, so different harmonics order up to the 20th harmonics order. So you can see the fifth is a dominant here, seventh is also dominant here, then 11th harmonics is a dominant, but the third harmonic is nearly equal to 0 because it is a three-phase circuit. So phase angle, corresponding phase angles are displayed in the fourth window. So likewise we can implement the DFT for a phasor calculation, and from that we can do the harmonic analysis. So how to generate the fantastic report out of this? So you can go into the program again. Here you will find the publish. In this publish, you can edit this publish with the PDF file. So it will directly current output format is a PDF. By default it is HTML. You can change it to PDF. So by default it is HTML. I'm changing it to PDF and I click on publish. So it will give you the fantastic report from these publications. Okay, so first time it will display the figure again and later on it will open the published file. So wait for opening of the published file. So let's see the path where it is stored. Okay, still it is working. This will be this is now the command is activated. So first time it will take the time to publish the report. Okay, so now this report is published. Here you can observe the DFT for phasor calculation. So first row data, all data is displayed because I have not given the semicolon there. Okay, so next time we'll give the semicolon, then DFT implementation, then THD calculation, total harmonic distortion is displayed, then plot, and the plot graphical window is also displayed over here. So let's hide this X with the semicolon and once again publish the report. Okay, so my PDF is open, so it is not. So close the previous PDF, then only it will publish. If you not give the semicolon, that will be appear in the published report. So if you give the semicolon at the end, then it will not appear in the publish window. Here I have not given the semicolon to L and N, so it will appear in the publish window. So let's wait. It is generating the output. So you can implement this DFT for the phasor calculation. So here you can see the table of content, converting raw data into column, DFT implementation, THD calculation, plots, first converted data, raw data into column data. So here length of the data is 641 and I'm using the endpoint DFT as 128 point DFT. 128 point DFT means 128 samples per cycle. So first we implement a DFT. See here the THD is 28.18%. In your case, according to the resistance inductance value, it may vary, and it displays the graph of the harmonics. So harmonic spectrum is available. With the DFT, we have calculated magnitude and angle of the current with respect to the harmonics order. So this is the first order, that is 50 hertz frequency signal, 100 hertz frequency signal. Here fifth order means 250 hertz frequency signal, 10th order means 500 hertz frequency signal. So likewise it will display the magnitude and angle plot. So you can implement in the previous video see the simulation, and in this video DFT for phasor calculation is implemented, which can be used for harmonic analysis. So you can prepare this harmonic analysis. Thank you.